Good morning. Good morning, everybody.
Good morning, sir.
Good morning, sir.
So let me just wait for some time for people to join in.
Sir, did you get a chance? Sir, Rohit from MTech CS here. Did you get a chance
Yeah.
to see the project, sir?
Yeah.
Project
So,
submissions?
yeah. So let me come to that question in some time. Let everybody join in. I will talk to you then.
Yeah. Yes, sir.
Okay. I think, yeah, it's time. So let's get started. So let me begin by making a couple of announcements, or perhaps I should wait for a little while for everyone to join in before I make announcements. Okay. All right. So
Sir, about the mid-sense course also.
yeah, so midterm scores we are correcting. We will give it by this week. Yeah, I will try to do that. So yeah, so all right. So Rohit, you were asking about the project, right?
Yes, sir.
So basically, so I was thinking because it's a reduced semester, typically there will be more time for doing projects. But now since it's a reduced semester, I was thinking that we will only have one project for the master students this time. So for the second project, for those who are interested, I will actually do that during the holidays. So if people are interested, I will make some videos. I will share it with I have your emails and I will share it with all of you, and you can implement that during your holidays. But for the things that will be evaluated as part of CS 561, which is the master's course, there will be only one project. So as far as looking at these projects are concerned, we have started looking at it, and we should try to do that before your end sems. We will try to give you feedback mostly. So that's what we will try to do. Yeah.
Sir,
So
I
any,
asked because after submission, the MTech students we were discussing amongst ourselves, we really enjoyed doing this project, and I think the majority of us, we were wondering if it would be possible to go back to the original plan and have another project instead of an end sem examination, or at least get the
so
option to do a project instead of an end sem exam.
yes, so that is actually doable, but the problem is this subject is important, and you will use it throughout, even in your master's thesis, and those of you who are going to do PhD. This subject is very important. So if you formally study the basics, it will be useful for you later. So I understand that there is a joy in creating a new thing and just trying to use what you have learned immediately. Okay, but in the long run, it will be
Yes.
more useful if you learn the concepts well. So that is why having an examination makes you read all the things once well. Okay, I will give you a
Yes, yes.
project, something similar for during the holidays. Okay, and I will we can have a discussion. For those who are interested, we can do that. All right. So yeah, so this is a conscious decision I'm taking, but see, right now typically what happens is, if you see the usual plan, there would be a recess week after midterm. So you were getting 1 week off that time, and then before your final exam there used to be 1 week for study. So all those things have been cut, and everybody is having a quiz and midterms and one after the other, and it is just getting too hectic for you. I can see that. So, and even though that's why I even extended assignment deadline, I'm not giving new assignment. So I want people to catch up and try to at least learn a little bit. So anyway, so that is the understanding. That is the thought behind what I decided to do. So yeah. Anyway, so anything else, Rohit?
No, sir. It's just that we're given so many quizzes and assignments, so everybody was saying let's like ask for a project instead of NSEM. But okay, sir. I mean, it's up to you, sir.
No, but you will find that knowing these subjects will be useful. So that helps. So Anyway, so it's just a thing that comes with experience. So you may not feel like that now. You may feel like you're stuffed under a lot of exams right away, but long term it will be beneficial. It is a benefit that you cannot quantify. The fact that you have gone through a full course with the and giving an exam, it is useful. So anyway, for the master student, you must know that there will be a separate assessment. So you will be graded amongst with your peers. All the master students will be graded separately. All the undergraduate students will be graded separately. So it will be fair in the sense that if you are having more work to do as part of masters, every master student will have similar work, and likewise, even if it is for even undergraduate students, if they are having too much work to do, since they are being graded with their peers, it is fair. Okay, so yeah, so now some announcements. So the last quiz we will have next week. So next Tuesday, quiz 5. Okay, so we will cover Markov chain and plus estimation. So something that I'm going to start this week. Okay, so this will be the topic for quiz 5. Then assignment 4, I will announce soon. I have been delaying it because some UG students told that they are having a lot of quizzes and assignments. So I thought I will. So I was originally planning to give 5 assignments, but I will make it only 4 assignments. So this will be the last assignment. So the next assignment that I will give will be optional. You don't have to submit it. It's just for you to learn. So that will be like a problem set. So that I will do anyway, but it's not mandatory that you turn in that, or I will not even evaluate it. It's just for your learning. So assignment 4, the last assignment will be fully on programming. Okay. So that's what that is. Then did you hear about the final sem dates?
15 to 20th on the college website, but no announcement regarding that.
Yeah. So let me just tell that right away what that is. So this is the tentative thing. So the college may change it, but if it doesn't, so let me just write that over here. 17th, yeah, Thursday. Okay, so let's just. So final sem exam will be on 17th December. Okay, it's a Thursday, and it will be from 10 a.m. to 1 p.m. So it's 3 hours. Okay, so this will have the same format as midterm. So you will have some. I will tell you the exact marks breakdown later, but for you as a guiding principle, there will be some objective questions. There will be then like your descriptive type questions, and then there will be programming questions. Okay, so all these 3 will be there, and as usual in programming questions, I will give you some code stuff which you can use to fill up. All right, so this will be the final sem exam and date and format. So this may change, okay, subject to institute approval. I mean the time. Okay, and regarding project for MTech, sorry, masters and /PhD, we will have this during holidays. Okay, so this, of course, that means that it is optional. So we will do this during holidays, something related to. Let me see what is good for you, but I am thinking of Kalman filters itself, but let's see. So I will announce this during the holidays. I will make some videos and then you can go through it and do it. Yeah, so that is about it. And are there any questions related to this?
I just wanted to mention that the deadline for the project had been extended by a few days. It was not reflected in Google Classroom, but like just so you're aware.
Yeah, I know. So that, don't worry. So those we even though it was not reflected in Google Classroom, we will account for that. So
Yes.
I see that a few students have not submitted assignment 3 yet. Please do it within next 2 days. Okay, I want you to finish it in next 2 days. You try to finish it in next 2 days. If you do it, submit it before Tuesday, we will not penalize. But after that, we can't say. So if there is some pressing issue by which you could not submit, let me know. Okay, so let me write this here. Submit assignment 3 in by, let's say, Tuesday night. Okay, so just don't skip the assignment. It has a lot of weightage, so just finish it by Tuesday night and submit it. Okay, those of you who have submitted late will not be penalized if you do it before Tuesday night. So there is one more day for you. All right, this can be done in that time. Okay, so are there any other questions, comments, or anything?
Sir, I have a doubt.
Yeah, please.
In assignment 3, there is a question which gave x and y as two Poisson random variables, and they ask the PDF of the convolution. But Poisson is a discrete one, right? So,
Yeah. That's a mistake. That's correct. So
Yeah.
Poisson, it is not PDF, it is PMF.
Okay.
So the question should read like using convolution, add it and get the joint PMF. That's correct.
Okay. Thank you, sir.
Yeah. Any other questions, comments? All right. So let us begin today's class. So sorry, I missed Markov chains plus estimation plus central limit theorem. Okay, all these topics: central limit theorem. Then weak law of large numbers. Then probability inequality, probabilistic inequalities. All these things will be included as part of the quiz. So anyway, it is not a very difficult topic. So again, all the questions primarily will be based on the videos. Okay, the question will be based on understanding of videos. So anyway, so let's get started. So this week, let's continue from where we left off last week, and let's finish up the central limit theorem portions, and then let's move on to estimation. So let's get started. So let's recap what we did last class. All right. So in the last class, we were trying to really understand some statistics. Okay, we were trying to understand things like probabilistic inequalities. Okay, we saw stuff like Markov, so which is probability that x is greater than or equal to a is less than or equal to expectation of x by a. Yeah. So similarly, we saw Chebyshev, which is probability that x minus mu. Okay, so this is greater than let's say some a is less than or equal to variance of x divided by a square, right? These kind of things we saw. This is Chebyshev. Okay, so yeah, all right. So these things we saw, and so it depends. After this, what we saw was weak law of large number. Weak law. So what we saw is Mn is an estimator for the mean, right? So this is x1 plus x2, xn by n. This is an estimator for the mean. Expected value of Mn is equal to mu. Okay, and what we saw in weak law is that Mn converges in probability to mu. Okay, and what does that mean? The error that Mn, the estimator Mn error makes. So this is the error, right? So if you choose a error level, Mn minus mu, if it is greater than or equal to some epsilon, let's call this epsilon as a error level. Okay. So the error, given that there is an error level, as you increase the number and more samples, the error probability will go to 0. This is what is meant by convergence in probability. Okay, so this is what we saw last week, and we also just began the topic of central limit theorem. So let us start from there and let's finish some of the things that we couldn't do last time, and then move on from there. So we saw central limit theorem. So what we saw is several versions of it. So we said if Sn, so let's say Sn is equal to x1 plus x2, just the sums. Okay, so we know that expected value of Sn, this we have learned. Okay, so and is equal to n mu, right? This we saw because of the linearity, because we are saying xi's are IID samples, independent and identically distributed random variables. Okay, IID samples with mean mu and variance sigma squared. Okay, so using that, so this is the first thing that I'm stating is the informal central limit theorem. Okay, so what we saw is the expected value of Sn is n mu, and variance of Sn is n sigma squared, right? This was what it was. So this is these two things you get from whatever you have learned earlier. Okay, but the informal statement from central limit theorem is telling you that Sn, you can treat it almost like normal distribution. Even though it is not normal distribution, you can treat it like normal distribution with mean this and variance this. Okay, so this is one version of central limit theorem. And then we also saw, suppose instead of looking at Sn, we look at Mn, which is the estimator for the mean, okay, which is going to be Sn by n. Okay, the expected value of Sn is going to be mu, okay, and variance of Sn is going to be sigma squared by n. Okay, but here central limit theorem informally states that you can treat Mn as though it is normal, okay, with mean mu and variance sigma squared by n. Okay, so this is the new thing. You already know whatever is there in these boxes. This is known. This is known from prior classes. These things you know. But the new thing is treating, even though Sn is not normal, you can treat it as normal and you can get answers by treating it as normal. So that is something that is new. This is going to be a central theme in next two topics. One is parameter estimation, and it's also going to be important in hypothesis testing. Okay, this idea that even though you are doing xi's need not be normal, okay, xi's need not be normal, but Sn will behave like normal. And even though xi's are not normal, Mn will also behave like normal. So that is the new thing that central limit theorem is teaching you. Okay, and yeah, somebody has a question?
Sir, that second box, is it expected value of Mn?
Yes, I'm sorry. Yeah, this is expected value of Mn. Thank you. Yeah, because we are discussing Mn. Yeah, thank you very much. Yeah, this is Mn. All right. So now, so these things having given you these results, informal versions of central limit theorem, let us try to apply it for the things that we couldn't do last week. But I think it was kind of a simple, silly mistake that we were doing. But any case, let's just do that. So let's go to Sitsikilis' example and look at this. So this is the part. So let's just copy this over. What is happening? Why is it not copying? Tool sheet, print screen. Okay, some reason it is not copying over. But any case, let's write that. So example from Sitsikilis. So there is n is equal to 36. So there is going to be, it's a binomial. Okay. So what is binomial? Binomial is like you are doing n trials. Okay, it is actually going to be sum of x1 plus x2, and you are counting the number of trials, right? So this is binomial. I hope you remember. P is equal to half. Okay, and the question that they are interested in, probability that, so this x they are calling it as Sn, okay, because that's sum of n thing. So probability that Sn is less than or equal to 21. So that is the question that we are trying to answer. And the usual answer that is given here is the usual binomial thing. What is that? So that is 36 choose k, half to the power of k into half to the power of 36 minus k. Okay, and k goes from 1 to 21. So this is the exact answer. Okay, now what are all the values SN takes? So since it is sum of 36 Bernoulli trials, okay, each of this is an independent coin toss. The binomial actually, if you plot it right, the PMF, what it will see is you will see that it has points at 1, 2, like this, 3. At discrete points, there will be mass. Then, somewhere you will have 21, 22, all this way, something like this. Okay, so it will have mass in discrete. And basically, now we can use central limit theorem and say that this is approximated well by the central limit, the normal distribution. That is what we are saying. Okay, so that is what central limit theorem says. Okay, so basically from central limit theorem, what do we have? We have that Sn can be approximated as normal distribution with mean. Okay, so what is the mean of binomial? Expected value of Sn, what is that? So that is NP. Okay, so that is going to be 18. Okay, and the variance of binomial is going to be NP into 1 minus P. Okay, so N is 36. This will be 1 over 4. This will be 9. So the variance will be 9. Okay, you can treat it like this. All right, so this is sigma squared and this is mu. Okay, now if you note right, there are 3 possible ways in which you can approximate Sn. So possible approximations. So probability that Sn is less than or equal to 21 is also approximately equal to probability that, so this thing we will call it as Xn. Okay, so this is the normal distribution with mean 18 and variance 9. We can treat this as probability Xn is less than 21. This is one approximation. Okay, or you can also approximate it as probability that Xn is less than 22. Why is that? Exactly less than, okay, strictly less than 22. Why we can do that is because Sn does not take any value between 21 and 22. There is no points that Sn will take any probability. Okay, so you can approximate it this, or you can do the best approximation, which is the midpoint. What that means is you can say Sn less than or equal to 21. You will approximate it as probability Xn is less than or equal to 21.5. So that is in between these two. Okay, so let us try to do all the 3 and let us try to compare. Okay, so let's do that right away. So the exact answer that is given by in the lecture notes of Setsikis is 0.8785. So let's try to do this for this. So now this Xn, it's a normal distribution with mean 18 and variance 9. Okay, this is also equal to the standard normal thing, right? So what is that? This is equal to the standard normal table phi of 21 minus 18, the mean, divided by variance. Variance divided by standard deviation. So variance is 9, the standard deviation is 3. So this is equal to phi of 1. Okay. Yeah, so phi of 1. So what is that? So we can actually go to the standard normal table here and see that. So phi of 1. So this is 0.8413. So this is one approximation. This is 0.8413. Or if you want, you can do the other approximation, which is phi of 22 minus 18 divided by 3. Okay, which is going to be phi of 1.3333. Okay, that approximation gives you, so if you do 1.333, 0.989082. Okay, the third and the final approximation, what you can do, you can treat it as phi of 21.5 minus 18 divided by 3. Okay, so I hope you remember what is phi. So what is phi of z? So this is equal to probability that standard normal table z takes a value less than z. Okay, so this is I hope you remember, this was asked even in assignment. This is standard normal table. Okay, so what is this? So this will be 3.5. It is phi of 3.5 by 3. Let's do that. So this is going to be phi of 1.126, something like this. Okay, so what is phi of 1.166? So that's what we need to see. 1.166, something like this. So 0.877. So this is the entry. Okay. Okay, now you can see which approximation is doing the best. So this is the original value. And if you see, this approximation is giving the best answer. Okay. So this is what we got kind of confused in the class last time, but I hope now this discussion is clear. Are there any questions here?
Sir,
Yeah.
the xn is the normal distribution, right?
Yeah, xn is a normal distribution given by this. The mean is 18 and variance is 9 square. How did we get this? Is because we have seen the central limit theorem informal version, right? So the, yeah. Okay.
I understood that. The doubt I had was, here we are approximating that p of xn less than equal to 21 is approximately equal to p of xn less than 22.
No. I'm saying this is a approximation 1. Okay, this is approximation 2. I'm trying different approximation.
Okay.
So this is approximation 1. Okay, so we are just trying out because since Sn does not take any value between 21 and 22, I'm trying out different possibilities. I can try out 21, I can try out 22. Does that so whoever asked it, did it answer your question?
Yeah, I got confused about it, that how
okay. It is not that I'm saying these are equal. All right.
Yeah. Thank you, sir.
Anybody has any other questions? So this is the third approximation. Okay, good. So that's good. So I hope now you can see that there is the central limit theorem is giving you a lot of interesting shortcuts to what would have been this is a cumbersome computation, right? This would have been quite difficult for you to compute. Okay, and this central limit theorem gives you a shortcut. Okay, so let us see one more example what Sitzikilis gives, and so let's see that. So the next thing that yeah, please go ahead.
In the case where xn is less than 22,
yeah,
you have written that phi of z is p of z strictly, less than or equal to z, whereas there we had it is just strictly less than 22. So can we use the phi over there?
Okay, so that is okay, I understood what you're asking. So what you're saying is we have used this, right? How can we use phi of 22 minus 18 divided by 3, right?
Yes.
That's your question.
Yeah.
So now, because why do you ask that? Because phi is typically this PDF, so it should be used only with less than or equal to something, right?
Yes.
Yeah. So now coming to what is the distribution of xn? What is xn? Xn. What is xn? Yeah. So it is normal. Okay, with mean 18 and standard deviation 9. So since it's a normal distribution, which is a continuous distribution, these two are equal.
Okay.
So that is why I hope it is clear. I understand the confusion. You should not be doing it, but since it is normal distribution that you are considering, it doesn't really matter whether or not you include 22 or don't include 22. Okay. So these are the two extremes that you can approximate, and it turns out that both extremes are not good. The best value you will get is by taking 21.5. That is the point that I'm trying to tell.
Yes, got it. Thank you.
Okay, now using the same idea, there is one more example that Sitzikilis is explaining. So in the same example, what is the probability that Sn is equal to 19. Okay, so now whatever you asked, I think it was Tanuja, but whatever you asked here, right? If you see probability Sn equal to 19, if you approximate it as probability Xn equal to 19, where Xn is your normal distribution, you will get the answer as 0, which is clearly not the case, because you know this binomial takes a value for 19. So this is not a good approximation. So this is not good approximation. Okay, so what instead he recommends is to use that this is approximately equal to probability that Xn takes a value between 18.5 and 19.5. Okay, so this is a better approximation, and let's try to do this. Okay, so if you want to do this, so this is going to be f of Xn of 19.5 minus f of Xn of 18.5. Is that all right? Because this is the CDF of Xn. I can do this way. Okay, so let me know if you are having any confusion in this. So then what you can do, you can write it as 19.5 minus 18 divided by 3 minus phi of 18.5 minus. Okay, so this way you can simplify. So this will be phi of 0.5 by 3. What is that? So that is going to be 0.1666, I hope. Yes, 16666, so on. Yeah. Minus phi of.
So it's 1.5 by 3.
Oh, 1.5 by 3. Okay, I'm sorry. So this is going to be 0.5. Yeah, and this will be 0.16666. So let's use that and try to compute it. So what is phi of 0.5? Again, we go back to our table and pick that up. So phi of 0.5. So it's over. So anyway, where is this? Here. Okay, it is 6915. Minus 0.1666, right? What am I doing? I'm doing some, 0.1666. So 6, this one. Okay. Perhaps this might be a better choice. Anyway, so let's just take one of them, 0.5636. And if you subtract these two, I don't know what that is. So let's look at what Sitsikili says we get. Okay, he has taken 0.5675. But anyway, so this is approximately equal to 0.124. So this he takes it as 0.17. And this number is, yeah. Because you know 0.16666, if you have to approximate, it is closer to 0.17 rather than 0.16. Okay, so this is a better approximation. So that is why he has taken this. But anyway, this number is 0.124. Exact value for this, if you do the exact computation. So for Sn equal to 19, what is the exact value? So it is 36 choose 19 into half to the power of 19 into half to the power of 17. Okay, this is the exact value. Then this actually turns out to be 0.125. Okay, so 1251. So basically what we are saying is even this approximation is doing well. Okay. I don't know if I went through this fast. So if you have any questions, please ask. So can I just have a poll? Can everyone just say if things are okay? Okay, very good. So that's about it. So this finishes. Okay, there is a discussion here which we have to have. But anyway, so let's do that now. Okay, so far what we have seen is the informal version of central limit theorem. So let me complete it by telling you the full proper technical version of central limit theorem, the formal version. Okay. So whatever you have, if you have understood this so far, the next thing will be very easy. So let me just say the formal statement. So let's keep the informal statement here for benefit, just to understand. So we saw informally, we saw that this will be normal n mu, and this will be n sigma squared. This is the informal, and mn we saw, we can approximate it as normal, mu by sigma squared by n. Okay, so now if I let n tend to infinity, these two statements does not make sense, right? If you really see, if I let n tend to infinity, these two statements, this will become normal infinity with infinity. That doesn't make sense. Here it will become mu, and this will become 0, right? Sigma squared by as n tends to infinity. Okay, the above two informal statements break down. These statements break down. Okay, you can see that, right? Why? Because this first one will become Sn will be normal infinity infinity. That doesn't make any sense. Okay, similarly Mn will become mu, and this will become 0. Okay, so as n tends to infinity, these statements break down. Okay, so that is why there is a formal version which does not have this problem. Okay, the ideas are here. If you can understand these two, we are done. But as n tends to infinity, there is no clarity as to what is happening. Okay, so that is why we have formal statement of this. So let us talk about that. So for that, we have to first understand what is called as convergence in distribution. Okay, so now what is meant by convergence in distribution? So basically, let Zn be a sequence of random variables. Okay, so basically these are all random variables. You can think of, instead of Zn, you can think of Sn or Mn. Okay, whichever thing, basically it is a sequence. Okay, so some estimator or something like that. It's a sequence of random variables. Okay, we say, so this is a definition I'm giving you. We say Zn converges in distribution to another random variable Z, okay, and which is denoted by basically Xn. Zn converges in distribution to Z. Okay, when for any C, okay, no matter what C you choose, probability that Zn less than or equal to C, this, what is this number on the left hand side? Yes, what is this? Can someone tell me what this is? When what do you denote probability Zn less than or equal to some number? What is that called?
CDF.
CDF.
Yes, that is a CDF. So basically we are saying Fzn of C, that is CDF. Okay, for any C, the CDF for Zn, right, it starts approaching the CDF of Z. Okay, this is Fz of C. Okay, so that is the whole idea. Do you understand? So what do you mean by this? So if you start, let us say your Z has some CDF like this, okay, like something like this, and your Zn's, no, Z1 will be like this, Z2 will be like this, Z3 will be like this. So CDF, okay, this is a bad diagram for CDF. CDF increases, so let's not do this. Let me take a more realistic explanation. So what I'm saying is, let us say there is some, this is the CDF of Z. Okay, so this is Fz of C, this curve. Now, what you are saying in convergence in distribution is that Fz1 may not look like this. Okay, Fz2 may not also look like this. But slowly, you are approaching the Fzc. This is Fz1, this is Fz2, this is Fz3. So slowly, as you keep increasing n, okay, you are going to get closer and closer to this. This could be Fz 100 of C, something like that. Okay, so this is C, and this is 0, and this is 1 somewhere. Is this idea clear? So do you understand what is the meaning of convergence in distribution now? Okay, let me just again go back to the board and ask, So is everybody understanding this convergence in distribution? Is it okay? Can I have a quick poll? Yes, very good. So basically the CDFs of Zn, right? These CDFs, they are beginning to look more and more like CDF of Z. Okay, now given that we have defined this mechanism in place, now we can define the formal version of central limit theorem, which we will do right here. So what formal version? So we have essentially xi's I from I greater than or equal to 1, okay, is IID samples from a distribution which has mean from a distribution with mean mu and variance sigma squared. Okay. Now what we are saying is central limit theorem states that the random variable Sn, which is given by you know what is the definition of Sn, let me not repeat. The random variable Zn, which is equal to Sn minus n mu by square root n sigma. Okay, this Zn, okay, this Zn, the random variable Zn converges in distribution to, important, right? Converges in distribution to normal 0, 1, okay, which is typically indicated by Z. So basically we are saying Zn converges in distribution to Z. Okay, let me repeat. So what we are saying is you have xi's, which are IID samples from a distribution with mean mu and the variance sigma squared. Okay, this much all of you understand. This we have been seeing even in the beginning, right? Right in the beginning, in the informal version also we have been seeing. There are IID samples, each IID samples with mean mu and sigma square. So this you have seen, you know what is Sn also. Now what we are saying is, so instead of looking at Sn, so in the informal version we said Sn looks like normal, Mn looks like normal. So in the formal version what we are saying is don't look at these two, instead look at Zn, where Zn is given by Sn minus n mu divided by square root of square root of n sigma. So if you look at this, okay, this is some random variable, right? Sn is a random variable. These are all constants. So if you do this, you will get some random variable, which is Zn. Okay, now what we are saying is this Zn itself is going to converge in distribution to normal 0, 1. Okay, so in order to understand this, let me just ask a few questions to the class. Okay, what is the expected value of Zn? Can someone tell me?
Zero.
Yeah, so it is 0. So basically it is nothing but expected value of Sn minus n mu by square root n sigma, right? This is what we know. This second part and the first part, all of this is constant. So what it ends up becoming is expected value of Sn minus n mu divided by this, right? So now expected value of Sn is n mu. So this is 0. Okay, so that much you understood. Very good. So now what is variance of Zn? Okay, let me ask this before we go there. So let us say you have x, whose x is there. There is a random variable x with variance sigma squared. So let me ask, what is the variance of ax plus b? Can someone tell me this?
A square sigma square.
A square variance of x, which is nothing but a square sigma square. Okay. Now, similarly, you try to answer what is the variance of Zn. So variance of Zn, if I do, this second part is a constant. So we don't bother about that. So that is going to be, this 1 over sigma square root of n, that's we have to square it. Correct? And then we have variance of Sn. That's all. Correct. So now what is this going to be? This is going to be sigma squared and n. All right. And what was variance of Sn? If you remember, it was n sigma squared. So variance of Zn is also equal to 1. Okay. Is this clear? So basically why did we do all this? Basically to show that this entire complicated thing is just coming to make, if you took the original informal version and if you let n tend to infinity, this was giving us a very weird situation. Okay, we were not knowing what we should do, because the normal, if you let n tend to infinity, this becomes normal infinity, which is not really clearly defined. To make sense of it, to write it formally in a consistent, mathematically rigorous way, what we did instead is to look at some other random variable. The random variable was so constructed that its mean and variance was 0 and 1. Okay, so then now you can say as n tends to infinity, it converges to in distribution to standard normal. So this is now well substantiated. Okay, but what I'm trying to say is this is something that is already discussed in the informal thing. All right. Okay, so let me pause here for questions. Are there any questions? Ramnath?
No, sir.
Okay, so that's good. So if there are no questions, then let me briefly introduce the next topic. It's a small topic which is called estimation. And then we will continue this topic tomorrow. But this idea, the central limit theorem, is very important. It keeps coming all the way till the rest of the course. So please, if you have any questions, you have to ask now. Even though you may feel it's trivial, it is important. You can ask. All right, so let's move on then. So the next topic we are going to talk about is called estimation. So we have already seen one estimator, right? So estimation. This is okay. Now this particular topic is going to be different from what Sitsiklis teaches, and why I'm doing that is because Sitsiklis's treatment of inference and estimation is very theoretical, and it is not going to be very useful immediately. So this is a new topic which is completely based on what I am going to follow is this book. So this is called, there's one textbook. This is chapter 7 of the textbook called as Introduction to Probability and Statistics for Scientists and Engineers. Okay, this is Sheldon Ross. So this book is, if you search in internet, this book is available. You can download it from internet and you can see chapter 7. So in chapter 7, we are going to omit some portions. I will let you know what those portions. So typically the portions which starred portions will be omitted. Details to be announced soon. Okay, I will details to be announced. Okay. So this is the new thing that we are going to start discussing. We won't discuss fully the chapter 7 completely, but we will discuss a major portion of it. The portion that is relevant for you to learn machine learning, that portion we will discuss. Okay, so let me just move ahead. Okay, now what have we been seeing so far? So far, what we saw, we have a probabilistic model, right? We have a probabilistic system. No, what do you mean by that? So we have looked at, for example, coin toss. We know what is the probability of getting a head, right? So given the probabilistic model, we are trying to come up with outcomes. Like we are going to see what outcomes we get. Okay, and then we'd say, okay, these outcomes came because this probabilistic model was this, and we can talk about probability of some events. This is what we saw. We saw so this was one way, and then we also saw this through the lens of random variables. Okay, so basically what we have is there is a model. Okay, there is a model, and then there were some measurements, and then what we got was random variables, right? We had random variables, and then we asked questions on the random variables. This is what we did so far. Okay, now if you have to flip this, okay, this is not how real life will be, right? You don't, in real life, nobody tells you the probabilistic model. How does real life look? So in real life, what we have is we have to do other things. You have outcomes given. You have outcomes, and then you have to basically arrive with, you have to come up with probabilistic models. So why do you want to do this? So why is this useful? Because this lets you do basically things like inference. Okay, which means you want to be able to predict things. Okay, inference, prediction. Okay, these things you can do based on, once you learn the probabilistic model, then you can predict what is going to happen in the future. Okay, that is why it is important to look at the outcomes and come up with probabilistic model. So, okay, that is the idea of this estimations chapter itself. Okay, so it starts off easy, but then slowly, if you keep building on it, you come to the heart of machine learning at some point, or statistical pattern recognition, statistical learning theory. All these things are coming from here. Okay, so this is what we are going to try to do in this chapter. So let's do that. So let me ask a simple question to start with. So there is a coin. So coin with unknown bias. Okay. So now let us say the coin gave this. So the outcome, the coin with unknown bias. So we saw some observations of this. We saw that it gave a head, then it gave a tail, and it gave a tail. Okay. So now the task is to predict the bias. Okay. So of course you will say this is going to be 1/3, because 1 out of the 3 times this was giving a head. So this is 1/3, you will say. But instead of trying to directly arrive at this, what we will do is we will basically try with different values of bias. So let us say P is equal to 0. So what does this mean? This means that the probability of getting a head is 0. Okay. So now what is the, given that P is equal to 0, what is the probability that you will get head, tail, tail? What is this going to be? Can someone tell me? I'm saying the bias is 0. So there is no way you will get a head. Okay. So what is the chance of getting this?
0.
Very good. So let us similarly try one more extreme. P equal to 1. What is that going to be? We are saying that it will always give a head. Okay, now what is this going to? So this is a strange notation. Okay, this is also going to be 0. So okay, so this, let me just be clear here. So when I write HTT, and this is not conditional. Okay, it's basically, if you want, if you can write this as HTTT with semicolon. Okay, so basically it means parameterized pi. So this is a problem which people have done. This is typically, you know, this as conditional distribution, right? So this is not conditional distribution. Okay. All right. So let us try one more before we come up. So what is probability of half? If we do, what we will get?
1/8.
1/8. Okay, so basically why did we do all this? If you really plot this, okay, if you plot this function, we will say fx of p. So fx of p is a notation that they use, is also equal to p of http. Okay, if you plot it as a function of p, it will be 0 here. It will be 0 at 1, okay, and it will have a shape like this. Okay, and it will take a peak at, what is the value it will take peak? Somebody wants to guess?
Half.
Half, sir.
Not half, 1/3. Because you got one head and two tails. You can try it out. Okay, you can do this in your in your Python, and you try it out. It will give at 1/3. Okay, so this is called as the maximum likelihood estimator. So what it is trying to do. Okay, so let's not dwell into too much of this, but the idea was, you try it out at home. You look at this sequence of outcomes HTT, and you plot for p equal to 0, p equal to half, p equal to 1/3. All these values you plot, and you generate this figure. Okay, and then you try to see where the maximum is coming. It is coming at 1/3, and the reason why it is 1/3 is easy, because if you look at these coin tosses, 1 out of the 3 were heads. So that is the actual thing. So that's why it peaks at this, and this estimator is called as maximum likelihood estimator, and we will do more of this in the next class. But yeah, so are there any questions for this estimator business? Okay, are there any questions in general? Is everything okay? Yes, can I have a quick poll? Okay, so that is good. So let's just stop here, and we will continue on this topic tomorrow. All right. So have a good lunch. Thank you, everyone.